Hello? Oh. Hi, we started. Thanks. Okay, that's me. 15 years ago, when most of you would probably were already quite skilled hackers or security researchers, my dream was to become a mathematician. I was studying mathematics at a university in the Netherlands and following lectures on, among other things, elliptic curves, which I thought then and still think is one of the most beautiful areas in mathematics. Now, life doesn't always go as you plan, and in 2015, I'm not a mathematician. I work in IT security, but these elliptic curves, they do play a role in security, namely in elliptic curve cryptography, which means that I'm really excited to be talking about this because it does feel like meeting a long-lost friend. And I'm also very honored that people voted for this talk, so thanks for that. Before I start, a few disclaimers. Firstly, you're not going to learn anything in this talk that you can actually use. Cryptography is hard. Elliptic curve cryptography is not necessarily harder because that's subjective, but it requires 1 or 2 years extra of mathematics, which you can't squeeze into a year. You definitely can't squeeze it into a 45-minute lecture. If you were expecting to learn anything useful, you probably should go to one of the other rooms. I also don't want to stand here pretending I'm a cryptographer. I understand the math because I used to do that. I could implement the algorithms, but I'm a sloppy programmer, would probably make a few mistakes. I wouldn't be able to find fault in other people's mistakes, and I don't know all the details of the research, what to look for in implementations. And finally, this talk is really aimed at people who don't have a much understanding of mathematics. So I skip over some of the gory details. If you happen to know a bit about elliptic curves, you notice this, and I apologize for that. I think it's more important that everyone just understands what's going on. Whenever you see or read read an introduction into elliptic curves, they always start by saying, well, it's something that satisfies an equation y squared equals x cubed plus a times x plus b for some a and b. And that's also a prime number because this is crypto and there are always prime numbers. I think this is confusing. This is completely irrelevant for just to have a basic understanding. But what is important to know is that there is a choice to be made. Different A, different B, different P give different elliptic curves, some of which are better than others. So there's not just one elliptic curve. There are an infinite number of elliptic curves, and one of the problems is which one to choose. What is more important is to know that an elliptic curve is something that looks kind of like this. And you see the curve, you see the x and the y-axis at the background. And on this curve, there are a very large number of points. And it's these points that play a role. Now, computers can easily represent these points by their coordinates or just by numbers. And in this talk, I will assume that points are numbers. And this is more or less true. That's one of these details matter a lot because that's where you could make mistakes. But I'll just assume that a point is represented by and represents a number. The most important property, or one of the most important properties of elliptic curves is if you take 2 points on the curve, P and Q, and you take the line through P and Q, there's always one line, the one such line, then there is a unique third point on the curve on this line. And a second important property is that the curve is, as you can see, symmetric in the horizontal axis, the x-axis. So you can take the vertical line through this and you get another point on the curve. And this point we call P plus Q. I can't emphasize enough that this is not supposed to make any sense. This is just a definition of, you define P plus Q this way. If you're studying mathematics and you learn about elliptic curves for the first time, which would make you a minority because it's within mathematics, it is a bit of a niche subject. If you would learn this, it wouldn't make sense either. There is a bigger theory behind this, but this is like even more advanced math. And this is what we call point addition on elliptic curves, which means for every 2 points on the curve, for every 2 P and Q, wherever they are, we can define a third point, which we call P plus Q. That's another point on the curve. And the second nice property is if you take a point P on the curve, you may wonder, some of you may wonder, what if you want to define a point P plus P? Well, there's a unique line through P that touches the curve. It doesn't go through it. It's called a tangent line to the curve at P. This line is also a unique extra point that goes through the curve, that lies on the curve and on the line. And again, you can take the vertical line through it, and you find a point P plus P. And we actually call this 2 times P. And this is called point doubling. You can double a point. And you can combine it. You can get 2P plus P. Again, take the line through it, take the vertical line, and you get a point 2P plus P. And as you may have guessed, this is called 3 times P. And you can get 4 times P, and 5 times P, and 6 times P, etc. This is called multiplication, or integer multiplication. You take a point and a number, and you take the number n, you take n times that point for whatever n is. And this is the algorithm. Computers can implement it. And computers are very good at that. So, we can add points to each other. Take for points P and Q, we define the point P plus Q. We can multiply points by an integer. And it happens, and you don't have to worry about this, but this all satisfies nice properties. If you add P plus Q is Q plus P, etc. This means that the points form an abelian group. You don't have to know what it means, you don't even have to remember this, but if you're a mathematician or a cryptographer, this is extremely exciting. And mathematicians don't get excited very much. Now it happens that multiplication by integers is very fast. So if you get a point P and you want to get the point 100 times P, then the algorithm I just showed, which you can implement in a computer, you just add P 99 times to this point P. So you get P, 2P, 3P, 4P, until you get 100 times P. However, computers can do this much faster. And as follows. You take P, you double it, you get 2 times P. Next step is you add P to it, 3 times P. Double it again, 6 times P. Double it again, 12 times P. Double it again, 24 times P. Then you add P to it, you get 25P times P. Then you double it again, 50 times P, and double it again, 100 times P. So these are 8 steps rather than 99. If you start to multiply by integers of 50 digits or more, and this is what happens if you do elliptic curve cryptography, this is extremely fast. I mean, 8 or 99 for a computer doesn't make a difference, but we're really talking about many, many orders of magnitude. However, the other way around, which I call but isn't officially called division, is very slow. So imagine you have 2 points on the curve, P and Q, and you know that Q is n times P for some number n. It could be 100, could be 1,000,000, could be 17 quintillion, you don't know. Really the best way, almost the best way to find this number n is to start with P, then get 2 times P, 3 times P, 4 times P, until you reach the point that's Q, and then you know the number n. This is an extremely slow process, and as I mentioned, if n has 50 digits, this is just undoable for a computer, even for a fast computer, even for the kind of computers that I have in a data center in Utah. And this is called the discrete logarithm problem for elliptic curves. And it's this that is the basis of elliptic curve cryptography. The fact that multiplication is fast, but division or taking a logarithm, as it's officially called, is very slow. So the most important, or probably the most important kind of elliptic curve cryptography is the elliptic curve Diffie-Hellman algorithm, ECDH, and sometimes elliptic ECDHE, where the E is for ephemeral, but that's irrelevant for now. It's used in the following way, or to solve the following problem. 2 entities, let's call them Alice and Bob, because we're doing crypto. They want to agree on a secret key over a public channel. For example, Alice is a web server, Bob is a web browser. And they want to agree on a secret key so that they can encrypt their connection. There are very fast algorithms like AES, where as long as you have agreed on a secret key, then you can encrypt the whole connection very quickly, very fast, in real time. However, how do you agree? Because before you start encrypting, nothing is encrypted and anyone can read anything. So the algorithm is as follows. First, they agree on an elliptic curve to use, and as I said, there are many different curves, and the base point P on this curve. Alice then chooses a large random number A. She doesn't tell anyone about that. She just keeps it to herself. And Bob chooses a large random number B, lowercase b. Now Alice computes A times P, and even if A is very large, we've seen, or I've shown, or at least I've told you, that this is something her computer can do very fast. And she shares this number, this point, which is kind of a number, A times P, with Bob. Over a public channel, she doesn't care if anyone can read it. Bob does the same with his secret number. He computes B times P. B he keeps secret, but he shares the resulting point / number B times P with Alice over a public channel. Anyone can read it. Now Alice has been given B times P. She has this secret number A, and she computes another point, A times this point B times P, which is another point on the curve. Bob computes B times A times P, so B times the point that Alice has given him over the public channel using his secret number B. And they get a secret key because A times B times P is B times A times P. So they have agreed on a shared secret number, and the discrete logarithm problem means that no one can crack this, even if they can read, even if they know what curve is used, if they know the point P, if they have seen A times P and have seen B times P. You can actually see this in Wireshark. This is a Wireshark session from Firefox on Debian Linux connecting to the website of BSides London and over HTTPS. And Wireshark actually shows it. So the browser tells the server, well, I know a number of cipher suits. Cipher suits is a series of algorithms because in TLS or in HTTPS you need multiple encryption algorithms for different things. And the first 6 that are listed, they say ECDH or ECDHE, which is the algorithm I just explained. So this is the client, the browser, tells the server, well, I support these 11 algorithms in this order of preference. And the client also says, these 3 curves that are publicly known curves that defined in standards, these are the curves that I support. So if we're going to do elliptic curve Diffie-Hellman, use one of these 3 curves. And the browser responds, the server, web server responds, and they say, okay, one of these algorithms, indeed using elliptic curve Diffie-Hellman, and a number of other things. Let's go and use that. And then the server also shares, the server, I should have pointed out here, when the browser tells the server 3 curves that it supports, they have numbers, and one of them is hex 0017. And the server tells the client, okay, 0017, that's the curve we're going to use. That corresponds to NIST P256, which is a curve. And most of the other blue stuff, what you see here, these are the bits of this is a number, it's actually the point on the curve that they're going to use. No, sorry, this is not, this is the B times P that's shared in the public, the public point. And likewise, this is A times P for what the client tells the server. I guess this is a bit confusing, to which I apologize for. But my main point I'm making here is you can actually see this happen in Wireshark. Wireshark more or less tells you what's happening. You can actually follow it. you don't have to understand the crypto, the math behind it, or you don't have to know all the standards. But Wireshark tells you all this. So, okay, here's my point. And now they have agreed on a public curve, on a shared number. And you can't see this in the Wireshark because that's the whole point. I mean, the Wireshark can see what Wireshark does a man in the middle, but the whole point of ECTH is that you can agree on a secret number, secret key, while someone is listening in the middle. So, what could go wrong? And there are a number of things that can go wrong by choosing a wrong curve. As I said, there's a choice to be made for the curve, and there are good curves and bad curves, and good points and bad points. This is not a realistic example. This is something you can easily avoid, but just to give you an idea what could go wrong in theory. What if there's a loop? What if it happens that if you take this point P, and you add it to itself, etc., and 1001 times P is again the point P. I mean, it could happen. This means that 1002 times P is 2 times P, and 1003 times P is 3 times P, and 1,000,000 and 1001 times P is P again. There's only 1,000 different values of P. The algorithm still works, but someone trying to crack it has only have to try 1,000 different values for the points that they have to solve, which is trivial for a computer. And again, these kind of loops, they're easy to avoid. They don't happen. But this is the kind of thing that could, at least in theory, go wrong. And that's why you have to be careful. So loops can be avoided, but there's a large number of known weaknesses, curves you should avoid. And possibly there are unknown weaknesses. Things that no one knows, curves that no one knows are weak because no one knows the weakness, or curves that some secret agency knows are weak, but the rest of us don't. So I showed in this Wireshark session that we were using a curve called NIST P256. It's defined as follows by this equation with a very large number. This is the kind of large numbers you see in crypto. That's nothing strange. So it doesn't refer to the fact that this is a large number or a number that looks random. That's the whole point. But there is no good explanation of why NIST chose this number, this curve, which is a bit worrying. I don't think there's a backdoor or there's a secret algorithm, a secret weakness that NIST or their buddies at the National Security Agency know about, but it's possible, and I think we should avoid this kind of curves. And it's kind of worrying that this happens in between most elliptic curves. Crypto, when it's used to secure HTTPS, uses this kind of curves. And it's kind of worrying that no one wonders about it, that people aren't, apart from some people on IETF mailing list, people aren't really saying, hold on, we should choose curves that where we can explain all the, we should use curves where we can explain all the numbers. Okay, there's another application of elliptic curve crypto that I think is interesting, and that's random number generators. I've mentioned the word random a few times. Alice and Bob needed to choose random numbers. People need to choose, or computers need to choose random numbers all the time, and they need to be unpredictable and truly random. And that's hard, because by nature, computers are good at doing predictable things. Thankfully, computers have a bit of randomness. Things like how long it takes to write things to a hard disk, how long movements of the mouse, but that's never enough. Computers need much more randomness than that. So they use something called a random number generator, which is something that takes as input a truly random seed, so something generated by moving a mouse movement, hard disk read times, etc. Then it inputs it into some algorithm, and some shaking up happens, and it gives an output, a number, and sometimes, and this is why it's blue and red, sometimes part of the output is thrown away. And in this case, the blue output is the output of the random number generator, whereas what was the internal state is shaken up again, and it's another output and another output. And I really imagine this where you input a number, and then there's some kind of churning, and you churn out random numbers all the time. And this is what happens all the time in random number generators. This is how they work at a very basic level. I mentioned the discrete logarithm problem, which means that if you have a point n times p, that you can't find the number n. So that's kind of useful for random numbers, because you take the number n, which is, say, your random seed, and you take n times p, which is a new point / number. I said we could identify points and numbers, which looks really random. So you can make an algorithm where you start with a seed n0, you take n0 times p, this is a number n1, you take n1 times p, you get the number n2, etc. And the output of the random number generator is just a series of n1, n2, etc. So you start with a random seed n0 using a point p on an elliptic curve, and you get a nice random number generator. Well, there's one problem here. It is reasonable to assume that an adversary can read the output. Say they can read n1. That's not a bug, that's a feature of many random number generators. Random numbers are often shared. The problem is, if someone can read n1, they shouldn't be able to predict n2, n3, etc. However, of course, if they can read n1, assuming this is a public algorithm, which algorithms should be in crypto because we want things to be open, they can easily find the number n2, n3, etc. So this is not a good random number generator. But you can modify this a bit. And we take an elliptic curve with 2 points on it, P and Q, 2 different points. Again, we take a random seed. This is a real algorithm, so it's defined as a 32-byte seed, some random number, a truly random number, called S0 in this standard for some reason. And again, you take S0 times P, which is another number / point S1, and what you then do is this number / point S1, you multiply the point Q by this, you get another number point, 32 bytes, you take the last 30 bytes, you ignore the first 2 bytes, and this is an output of the random number generator. And again, with this S1, you multiply it this times, you multiply P with S1, you get S2, you get S2 times Q, you get another random output, etc. And because knowing S1 times Q doesn't give you S1, that is the discrete logarithm problem, this is a good algorithm. This is a good random number generator. And I should point out that this and the next slide ideas, the idea of this, or the way to explain this is copied from or borrowed from Dan Bernstein, Nadia Henninger, and Tanja Lange at a NCSC press conference last year. Now we had these 2 points P and Q on the same curve, and there's for a fact. This is a fact. This is a known fact about this curve, about many curves in general. There is a large number d, so that P equals d times Q. But you can't compute it because that's the discrete logarithm problem. Now let's show the algorithm again. This is just the same as the previous slide. And also note that there are only 2 to the power 16 possibilities. So if someone sees the blue bit, the 30 bytes as output, and again, that's a feature of random number generator, you sometimes see the output, then there are only 65,000 possibilities to get the whole output of S1 times Q. And that's actually very easy to compute because this needs to be a point on the curve, and it's trivial to, given the blue bit, it's trivial to find the red bit. And let's call this number R1. This number, which again can be easily computed. Now imagine someone knows this number D. So imagine someone knows the secret number D. Someone somehow had access to it. And again, pointing out you can't compute it. It's impossible to compute. Now, my claim is if you take R1, which is publicly known, and this D, which is secret, but except for to this person or entity, D times R1 is the same as S2. you can believe me that it's true, but I can even show it to you. S1 times P, which is S2, is the same, which is by definition S2, is the same as S1 times D times Q, combining the two yellow bits, because P equals D times Q. Because they work nice, you can change the order of D and S1, so the D times S1 times Q is D times R1. So I'll just show you that the red arrow indeed works. So if someone knows this number, secret number D, they can crack the algorithm. This is a big problem. So the question, the $1 million question, or the $10 million question, that's an in-joke, is, does anyone know this number D? Well, this is as I said, this is a standard. This is defined, you can read it, it's defined by NIST, and helpfully on the first page of the standard, it says the following acknowledgement. NIST gratefully acknowledges that and appreciates contributions by Mike Boyle and Mary Beige from NSA. Oops. As many of you will have realized by now, this is the infamous backdoor in dually C DRBG, the random number generator. And this is not just a theoretical problem. This random number generator was, through some social engineering and $10 million, made a standard in RSA crypto libraries. RSA as in the company, not RSA as in the algorithm. So that's a problem. And I think we all assume that the NSA does indeed know the number D. Right, conclusion. I haven't really explained this, but elliptic curve cryptography is important because we can do with much smaller keys. And that's the main advantage. Keys of 256 bits give more or less the same security using elliptic curve cryptography as 3072 bits RSA. And this also, they don't grow as fast, which means you can use shorter keys, algorithms are faster. This does make a difference as crypto is being widely deployed. There's one big weakness in elliptic curve cryptography, I think, and I don't think people realize this enough. It uses complicated math. It's great, it's fascinating, it's cool, but the fact that it uses complicated math doesn't make it stronger. Ideally, you would have an algorithm that uses very simple math that anyone who could do a bit of programming could understand, and not something where we rely on a very small group of people who really understand this, hoping that they're on our side, etc. And again, I'm not one of the people who understand this well enough to find algorithms, to find backdoors, etc. I don't think the group of people who understand it is too small. I think there are enough people, but it would be great if there were more. So yeah, tell your little sister or brother to study math and learn about elliptic curve crypto. That's it. That's me on Twitter. If you didn't like it, you can unfollow me.